Hello. Hi guys, good morning. So basically in this video we will see uncrossed line this problem. Firstly, it's a very good question. Some people have confusion. I will not name the particular type of algorithm, but some people have confusion. Okay, this algorithm can be applied or this can be applied. It's a very sudden confusion between greedy and DP. And also in DP, when they realize, then they cannot realize, okay, how can I relate to an existing problem? Cool. If even you can't relate to an existing problem, we will show you. See, it's very hard to exactly map from the previous problem of DP because DP has many variation. LIS, LCS, many like decreasing, increasing, consecutive, non-decreasing, non-decreasing, many. It's not important to actually remember, okay, which I have studied. If even you don't remember exactly what you have studied, and still if you want to figure out how you will do it, it is today in this video we're gonna see. So yeah, without further ado, let's start with the problem itself. Now, the problem says that very simple, very standard, uncrossed lines. We are given two integer array called as nums1 and nums2. We have to write the integers of nums1 and nums2 in the order they are given. Basically, nums1 is given, nums2 is given. Write that in the same order on two separate horizontal lines. As you can see, one line, another line. I just wrote it down. Now, we may draw connecting lines, which means connecting two numbers, lines, a straight line connecting two numbers, number 1 of I and number 2 of j, which means any take I and j, and we can, if they are same, I can just connect a line. And also the line we draw should not intersect any other connecting line. Let's say if I draw line right here, then I draw line between 4 and 4. I cannot draw line between 2 and 2 because I cannot choose a intersecting line. Okay, it is one condition. Cool. Note that the connecting lines cannot intersect even in the endpoints, which means it is not saying that okay, you intersect like this. Even if you intersect like this, it's also an intersection. So it should not intersect like this also. It should not be the case. Cool. Return the maximum number of connecting lines we draw in this phase. Basically, that those lines should not be intersecting each other. Cool. Now, let's see the example. Firstly, we look at the example. Okay, very good. 1 will connect. Okay, let's change the color. So 1 will connect with 1. Cool, very good. 4 will connect to 4. And I can see that, okay, it's finished. So maximum lines I can get is 2. Answer is 2. No worries. Let's see another one. Like 2, 5, 2, 5. I just drawn here. 2, 5, 2, 5. And you will see, okay, next is 10, 5 to 2. So initially I went on to 2, found a pair of 2. I went to 5, found a pair of 5. I went to 1. Okay, no 1 is there. I went to 2. 2 is found. So one thing which comes in my mind by seeing this example itself, okay, it may be greedy. What if I do is that, okay, I will start from I. And what I will try to do is, I will try to grab this j as what is the minimum j I can get after I have grabbed like allocation, which means I grab this I grab this j, both start from 0. I will just grab, okay, both of these I and I. Next my I is here and my j is here, right? I will just try to see, okay, what is the nearest location of 4 which I can get, because I'm just grabbing the greedy, most nearest location to me to actually reach to make a pair. And I will just try to make a pair like this, and ultimately maybe it is the answer, because I could see in the example itself it is what is like reflecting in the answer. First thing comes in our mind is greedy for this problem, but see, greedy you have before actually verifying and writing the code for greedy. Greedy can come in your mind, I'm not saying, but before writing the code for that greedy, just make sure that greedy is correct. Which means we will counterintuit our thing and we'll try to find an example such that greedy is not correct. See, why greedy was correct? Greedy was correct because I will look at the same example back. How? See, greedy was correct. Okay, let's remove this. Greedy was correct. I was just grabbing 2 and 2 from here. 5, I just grab 5 from here. Then again 2 and 2 from here. To make the greedy counterintuitive, okay, let's try to make greedy false. So I have to find an example to actually make, okay, now the greedy can't be applied. Then only I can move forward. For that, I just saw, okay, 5 was going on to the nearest next 5. Maybe I just remove this 2, and what if I just add these 1 and 2 before? Then I just remove this 5. So what this greedy would have done is, it would have just gone to 2 and then 5. So answer would have been only 2 lines. But what if I don't choose this 5 and I choose this 1 and 2? Thus, okay, I found an example that they see. First I thought of greedy itself. Then I counterintuited by finding an example. And how I found the example? By saying, okay, I will just try to apply greedy, and greedy was grabbing the maximum, like nearest element. Now just bring the forward elements back so that I can just make more pairs. Thus I just brought these back to actually make more pairs. Thus I can just try, okay, by the greedy way it is just bringing me 2, but if I just shift the example a little bit, then okay, 2, 1, 2 and 5, it should have been here, but I just dropped 5. I opt to not take 5, and then I get my maximum answer as 3, and the answer is 3 actually. That is how we thought of greedy first, and then we say, okay, greedy won't work at all. Basically at every element I have an option, I will take it or I will leave it. You saw at 5 I had option, either I would have grabbed it and would have checked, or I leave it. You have heard this before, right? Grab it, leave it, take it or leave it, yes or a no. Remember something? We have, for every element we have 2 options, take it or leave it. Remember, it's recursion, just have 2 options, take it or leave that element. Which means, let's look at the final example. It's also, you can see, it will actually make you think it's greedy because it's 1 1, then 1 1 2, and you found 2. But still, we thought of greedy first and then we figured out, okay, it's not a greedy thing. Cool. Now we know, okay, at every point of time I have 2 options. If I have these pointers here at these 2, then I can just grab them or I can just leave one of them. Now I can't make the entire recursive tree because it would become very big. Thus at a point of time, let's say my I is here and my J is here. Cool. Now at this point I have 2 options. Either I will just grab both of these, or what I can do is I will just grab this and I will just ignore this and will just move forward with this part, which means now my I is this and my J is this. Or else I can do is I can ignore one of them, which means I can ignore now I, and will I move, and now it will just compare these 2. So remember, either I will take that, which means I and J, I will just grab both of them, I and J, but it can only be grabbed if they are same. If they are not same, so how you will take it? As it was conditioned that you can only take it when nums of I and nums of J is equal, but it is not, so you cannot take it. Where it is gone? Yeah. So now you cannot take it, which means you have to leave one. So what you will do is else. Okay, now you will leave one. Now what I can do? I was at I and J, right? I was at I and J. Now let's leave J. So the J will move forward. You saw J move forward. Now, or one option is, now shall I leave I? So basically I was at 5. Now I just leave it. So I move forward. Right? J still remain there. Now you saw. In one case, I just leave one I, and one case, I just leave one J. Cool. Now, again, this part will again go to more recursion. That okay, this green part you saw above, if you are having confusion in seeing on the screen at one time, I've also provided the PDF of the entire notes which I'm showing right now. You can just go and open that notes parallelly to actually move through it, because it's the same. It is the green part which is actually going into further recursion. Now, again, I will check. Is I and J equal? Take it. No, I can't draw an edge. Sorry, I have to go to else, which means I have to ignore one of them. Cool. Leaving one of them, which means I will just, one chance, I will just ignore J. Cool. Now the J comes next. Oh, it is saying, okay, I will just have one option. Now, one option was to ignore I. Cool. I just ignore one of the I. I is ignored. Now I reaches here and then J reaches here. Cool. Other option for this part is, because see, we saw the recursion of this. Now let's see the recursion of this. Recursion of this, again same. It can be same also. So grab it. Same. Grab it. Cool. Now no else condition, because for sure it was same. I will just move both of my I and J forward because I have found same. That is because I wanted same, right? That's the reason. By this, you can just move on, going on the recursion. You saw what happened. At every point, I have I and j. I just choose. Shall I take it? Take it. Okay, cool. Shall I take it? Take it. Cool. Now I cannot take it. So basically, move j and in one step move I. Move j or move I. And thus by I can just bake on bringing my recursion. Now you will say, Aryan, you showed the recursion, but we cannot see any repeating sub problem. You told that okay, a DP can be applied when we have a repeating sub problem, but we could not see any repeating sub problem. Yeah, correct. It was hard to show in that example because it has some matching elements. But let's see with this example itself. At a particular point of time, let's say in this I have all different numbers A, B, C, D, E, F, G, H, right? All are different letters. Now, at a point of time, let's say my I and J is at my B and F. Not BF, but B and F. Cool. Now let's imagine. See, I have imagined that all of them like no one is equal, so that actually I can make your intuition like to show you that okay, we have a repeating sub problem easier. Now, if this I and J, so we saw okay, one option was to grab it. Other option was to leave one of them. Grab it was the only case when both I and J are same, and I'm assuming both are not same right now. I'm assuming to actually show you that okay, you have the repeating sub problems. Cool. Now, if it is not same, so basically one time my I will move, one time my J will move, and one time my I will move. Right? Cool. One time my J move, one time my I move. Again, remember, I am saying it is not same. That's the reason I am just grabbing only the leaving part. But also in the initially I showed you that okay, you have one option also to take it, but when they are same. Cool. Now in the again recursion part, it will just go and leave one of them. So J move forward. Again, I can move forward. Here again you will see that here the J move forward. Here you will see again the I move forward. Now you will easily see it is exactly the same sub problem which you will be solving by recursion. Thus, we saw okay, it's a problem of recursion. We saw the recursive condition also that okay, I will have my I and J pointer, and if it is same, I will just grab it, increase my counter by 1. If it is not same, then one step I can move my I, another step I can move my J. It is a condition. And also we saw okay, the problems are repeating, which means it is a repeating sub problem. Now we can apply DP for sure. Cool. Now let's see with the recursion part, then we will memorize it and then we will see okay, if some optimization is possible or not. Now recursion, simple as we saw, if it is equal, then just take it, which means just increase the counter by 1. If it is not, else, if it is not, then leave one of them. How to leave? Increase. If I was standing at I and J, then maybe leave I, so you move to I plus 1, or maybe you leave J, then you move to J plus 1, then you move to J plus 1. Thus, okay, if I leave one of them, so basically I move to I plus 1 or J, or basically if I leave J, then I move to I comma J plus 1. It is the same thing I will do in recursion. Let's see the recursive code. It's pretty easy. That how? Firstly, we call this recursive function, which will actually find the answer. We don't have to worry about it. Now comes the actual recursive function. That firstly base condition. If we reach the end, if the I and J are the pointers of the array, right? As simple as that. If they reach the end, no matter what, I can't find the answer, right? So simple. If any of the pointer reaches the end, just return a 0. As simple as that. Now have this counter condition as because we want to count the number of such connecting lines, right? Thus, okay, the first condition was to take it, but the condition was that both of them I and J numbers should be same. Cool. If they are same, so take it. Now if we just grab it, so the counter increase by 1, and also it will just go and count for what? I plus 1 and J plus 1, because I have grabbed both I and J, I am good. Else, if it is not same, then whatsoever counter you have, cool, no worries, take the maximum of I plus 1 comma J or J I comma J plus 1, which means here you ignored ith number, here you ignored jth number, and whatsoever maximum, by ignoring any of them, whatsoever is maximum, which means by leaving any of them, whatsoever is maximum, you just grab that. And that is how you will just return that count. But as we saw, it is just recursion and we see many repeating sub problems in it. So for sure, I will do a simple memoization. How? Just a 3-line change in the existing code. Nothing much at all. Firstly, I initialized a DP array with -1 of size n cross m, nothing. And then I just check, okay, if that DP array is not -1, which means that state of DP has been already computed. If it is already computed, just return that computed state. And how to actually know if that state is computed? While returning the answer, before returning the answer, just make sure to actually put that number in your DP state. That's it. Thus, this three-line change code will actually help you pass your solution. Exactly. How? Because now the time compression is nothing but O of n into m. Why n into m? Because at every point, at every combination of I and j, because you have an array of n size and you have an array of m size. Now, for this I and j, this every combination of I and j is being calculated only exactly once. Why once? Because of this DP state, which is actually taking your n cross m space. That is the reason you will just say, okay, the time and space is O of n into m. Now you'll say, Aryan, looks good. We thought of greedy, then we come to recursion, and then recursion would give a TLE. Then we actually found out, okay, we can memorize it, and we found the answer. But interview is asking me to actually optimize it. How to optimize it? See, if you have to optimize a DP solution, recursive solution can never be optimized. You have to transfer or shift that solution to a tabular solution, which is also called as a bottom-up approach. Memoized solution, which means recursive solution, can never be optimized. When we say optimization, it's mostly in terms of space. In terms of space, you saw that the space being taken is O of n into m, but we cannot optimize the recursive solution because we cannot visualize, okay, what's internally happening when it is being computed. Thus, actually, I will just start with this new approach, which is nothing but exactly same as above recursive approach. Exactly same we will do. We will just go on to I will just erase this part. We will just go on exactly same I plus 1 comma j plus 1, which means if we have, okay, I know I and j are same, I will just go on to the I plus 1 and j plus 1. If it is not, then I will just go on to I plus 1 comma j and I comma j plus 1. I can do exactly same. Just see, just as does that, I will use a tabular approach, which means I will just make my own matrix, my own this space, my own of this space I will make, so I can visualize, okay, how the space is being utilized. Now, cool. Now let's coming on to the tabular stuff and imagine the same stuff. What you were doing was, at any point of time, if you found, okay, the numbers are same, you found, okay, the numbers are same, then what you did, remember, 1 plus, you went on to the next one, which means I plus j, sorry, if you found, okay, I and j are the same, then you did 1 plus I plus 1 and j plus 1. You did this thing in recursion, but now we are moving from 0 to actually last n. So what I'll do, okay, this point, this I and j both are same, right? Now, one thing for sure, okay, these both are same. I will actually grab my value. I will do 1 plus firstly. I will do 1 plus. Now what? Shall I do plus 1? Plus 1, which means I am finding the value for this. Actually, in the tabular method, you go from left to right and then you keep on going at the bottom. So which means when you have reached at this point, at this cell, the answer which you have computed so far, let's imagine you have computed so far is nothing but of this cell right here, up till right here. So if you do I plus 1, j plus 1, it's nothing but this thing. So basically in recursion, it's been computed bottom up, right? Sorry, in recursion, it computes when it just gets reach the answer. But actually, when we are doing a bottom up approach, then we are finding the answer from this, which means I will say, okay, my D and D are same, which means, okay, what is the answer so far for A, B, C and F, G? Give me. And that answer is stored at this location right here. So I minus 1. So for this answer of DP of I comma J, I will have, if my I and J numbers are same, then it is nothing but 1 plus DP of I minus 1, J minus 1. That's it. If I said, if it is same, what if it is not same? What if it is not same? If it is not same, then as simple as that, as simple. Okay, I just erased everything. Lovely. Bahut acha. See, now if it is not same, what will happen is, see, if let's say it is not same, in this example I just showed you that okay, that green part will show you that okay, it is not same. My G and B are not same, which means my ith and jth number are not same at all. Now what I can do, I can just ignore maybe G. So if I just ignore G, then what I will get is F and AB, because I ignored G. F and AB is at the top. What if I ignored B? Then if I ignored B, then I will get a and a FG, which is at the left. So I can take the maximum of top and left to get the answer of this dp and I comma j, which is maximum of dp of I minus 1 comma j comma dp of I comma j minus 1. It is maximum of top, maximum of left. Why? Because I found out okay, they are not equal. My ith and jth character number was not equal. That is the reason I just found it. It's exactly same thing which we will do. And for sure you saw one thing that okay, I started my dp from the first index. Why? Because you saw when I am finding the answer for dp of I comma j, I am going on to I minus 1 and j minus 1. If I would have started from 0 itself, then I minus 1, 0 minus 1 is actually minus 1. I can't actually access the negative index, right? That is the reason I will actually start from the 1 index, which means I will start from here itself. My actual dp will start from here. It's just that okay, the last part will be initialized, means the indexes of entire I equal to 0 and j equal to 0 will be initialized with 0 itself, to actually make sure okay, when I am actually at this point and I want to access, maybe they are same, maybe both are a and a, right? Maybe both are a and a. So I want to access this element, which is this diagonal element. So it is, I can actually access it. It is 0. That is the reason I will just start my dp from nothing but 1 comma 1 and initialize my entire I can just initialize my entire dp with 0. But basically my whole purpose in mind is to initialize my ith row entirely and jth column, which means I equal to 0 and j equal to 0 entirely by 0, so that I can actually start my answer. That is the reason. Firstly, nothing much changed. Firstly, I just initialized my dp exactly same. It's just that okay, now the size is actually n plus 1 and n plus 1. I showed you above. Why? Initialize with 0. Nothing but it's because I want my I equal to 0 row and j equal to 0 column as 0. Nothing much. Now comes the interesting part. Nothing much going on from, why I'm saying nothing much? Okay. So going on from 1 to n, which means as I said, I will just go on from the first column up till the nth row. Okay, but is nth row from first column, and then from first column to mth row, mth column, right? From first, simple n cross m thing, right? From first row to nth row and first column to mth column. Now checking nums of I minus 1. You remember why I minus 1? I minus 1 is because see, I'm saying okay, what is the first character, first number, but it's actually a is the first number, but in the array itself its index is actually a 0. So I is now 1. But in nums, this a, which means the first letter, first start with 0, right? That is the reason I have to do I minus 1 to access the number itself. To access the number, I am doing I minus 1. So nums of I minus 1 and nums of j minus 1, if they are equal. So just take the diagonal value. 1 plus take the diagonal value. Now, else if they are not equal, then just take the maximum of what? Top or left. Just grab the maximum, and that is how you will build the dp array. And ultimately your answer, you for sure know it's stored in end, which means maximum of this and this part is stored in the end cell, and that is the reason you just return the n cross m. That is the reason your time and space exactly same, because you're just doing exactly the same thing. Where just earlier you was actually doing a recursive for which is actually going on to every combination of I and j. Now you are actually purposely going on to every combination of I and j and finding the answer. That's it. Space and time is exactly the same. dp space and dp time. Now, let's think how we can optimize it. Maybe we can, maybe we cannot. But now we can actually possibly start to think of optimization if possible. Mark on words, if possible. Now, if we just clearly go back, look and see, then we saw one thing. Okay, my I is moving and then my j is moving, which means for this row, I will just compute. Okay, for this row, I will just compute. For this, I will just compute. Now, when I'm computing this number, its value of dp, what I want only the top value, I want only the diagonal value, I want only the left value. Do I ever need this thing right here? Ever? No, right? Which means when I am on a ith row, I only require the content of I minus 1 row. As simple as that. Which means actually the row required will be only two, not only the above row and the bottom row. But actually we can do the same stuff in one row also, because as you see, it is just being overridden. Which means the content afterwards are not required for this thing, right? So I can just use only one row. Firstly, before being confused, firstly now you know that only two rows will be required, above row and bottom row. To actually find the answer for the bottom row, I only need the above row. You got that? Cool. Now I am saying not only rows are two, but actually I can do the same stuff in one row also. How? As simple as that, because for this number right here, I just need the value of this number. So let's say if this is the row, right? It is only one row. Now I will just and for sure, I just want the answer for this row, for this column, for this cell right here. I just want what was the, and I'm about to overwrite it. It is only one row which I'm about to overwrite. So before overriding, what is the value here? Now, what was the last value at this row? Because actually it was overridden. Now it was overridden. It had some value which it is now being about to override, and it is the value which is recently overridden, the last value. I will show you exactly what I'm saying. But one thing I'm just saying, okay, for sure, you can actually use, for one thing, you can use, just reduce your n rows space which you are using to actually two rows, and then I am saying not only two, you can actually reduce that to one row. I will show exactly how. But yeah, one thing okay, how you will just use O of n space, which means just one row exactly. Cool. Now, as I told you that, okay, just imagine that you have only one row, right? Now I will just write here. See, just take a snapshot of this, because I will just make it dirty, and again I will just come on it. I have only this row right here. Right now what happens is, I should myself take a snapshot of it. I will explain you guys, and then it will just become more dirty. Cool. Copy and then just do a simple paste at here. Just do it fast. Yep. Cool. Now we will come on to it later, but for now, let's see. You have this row, right? For this column right here, for this cell, firstly, if I just make sure, okay, this cell, it had some value which is about to being overridden by this cell, by the cell I, let's say DC. I will just not, I should have it as let's say MJF, Z. Cool. Cell ZC will get overridden by the cell GC. Cool. This cell had some value. Let's say X. If I'm about to find the value of this cell right here, so this Y will get overridden. This Y will override this X. So for that, I need to make sure, okay, I just get this value X at one place. Now, as you know, okay, this last number, let's say it was M. It overrided a number, let's say N. So although also I know that, okay, this M I need for sure, but also I need this N. So basically, M, before overriding my existing place, I will just grab this existing value. Okay, I will just grab, okay, what was N? Because M will override N in the next step. As I have moved to Y, this last value is actually being overridden by M also, right? Cool. Now M is here, N is not here. So I have to make sure, okay, I have the previous value, which was N. Also, I also make sure that before overriding my existing ith location, I should check, okay, what was the existing value at me? I have the X. And also I make sure, okay, what was the last value of me, which is the M. These three values I need to make sure, which means at this cell, I will take, okay, I am just calculating my dp of I. At this point, which means the above point, it is nothing but I will just have a variable called as current value, which I will have to grab before overriding that cell by dp of I, because I have only one cell, I have only one array, and it is nothing but I minus 1. Now I am finding the value at this I. So before finding the value, it had some existing value earlier. It is nothing but the above row value. That is, I will just grab, okay, the existing value, let's say it is named as the value which it already had as current value. Now this existing value, which was already overridden by my dp of I minus 1, it also had an earlier existing value, which was nothing but the last state before my dp of I minus 1 got overridden. What value was it was having? Let's say it name it as a previous value, let's say prev, which means before overriding my dp of I minus 1, what value it had. So I need this prev value, which is actually a prev value, which means before overriding my dp of I minus 1. And then for sure I also need a dp of I minus 1, because I need to have a left value. Thus I will just grab these three values from one row itself. If you have not understood it, just go and watch the same stuff again, and maybe you can try it also. But as the time has gone away a lot for this problem, that's the reason I will just move on. But I have explained very well, and I know that for sure, because I just put the same stuff to actually make sure that you imagine that exactly, that to actually override this dp of I, before that you get the value of this current value, which is nothing but the above cell value. The left cell value is nothing but your left cell value, and before overriding the left cell by dp of I minus 1, what value it had? It was the top left diagonal value. That is, let's say, prev value. In my code also, I just use the same conviction, prev value, dp of I minus 1, and this is nothing but current value. So you know that if you find the if you have found, okay, my I and j are both equal, so you will just do a 1 plus what? Prev value. If you say, okay, my nums of I and nums of j are not equal, so max of dp of I minus 1, which is the left value, comma current value, which is nothing but the top value. Exactly same you will see in the code, that if it is same, then 1 plus prev value. If it is not same, then dp of j minus 1, which, because I am just moving on j, dp of j minus 1 and the current value. And you see that, okay, at every time I am just updating my current value, my prev value with my current value. It is nothing but like this. And for sure I am just storing my current value before overriding my dp of j. Cool. As simple as that. Its prev value is for sure being overridden here by the current value, and that is how you will reduce the space to nothing but O of n only, or m only, whichever is minimum, because you are just grabbing the minimum part. If you just go and see, I'm just swapping whatsoever is minimum, because for sure if the number is 2, 3, 4, 5 and only one number is 2, for sure I can only have 1 point, right? So it's of no point to make an array this big. I can just make an array this big only, because whatsoever is minimum, I will make the array that big. Cool. That's the reason you will just get the complexity of O of n into m. Now you will say, Aryan, we saw from greedy recursion, memoized, bottom optimized, lovely, loved it. But if you just go and look back the recursion, it's nothing but longest common subsequence problem. Exactly same. If the people might have known it, but it's very hard to relate with 80 dp variations. I'm not saying to relate every problem with the dp variation, but maybe with the point of time, as you go on and see the problem, just make sure that you try to relate, okay, it is some kind of problem which we have actually seen, so that you don't have to repeat that same understanding stuff again and again. This same stuff comes in LCS also. The same stuff you saw above, that okay, how to visualize this tabular, again comes in LCS. So if you have seen LCS, so it's of no point to actually go and understand the same stuff again and again. It's the reason. The only benefit of actually relating problem with the existing problem is that you don't have to go on the optimization part at every step manually. You already know, okay, LCS has had all the optimization. The same optimization can be applied in this problem also. That is the only reason you have to relate a problem. I'm not saying to relate a problem to actually start solving it. Start solving the problem is actually thought of when we think, okay, it is recursion, it is having a repeating sub problem. Now it is a DP. Now to DP to optimize, if you had a old knowledge of okay the same problem, then you can actually have it a quick optimization and just do it quickly. Now the same problems which you can practice is edit distance, for sure, LCS, which is actually a standard problem of this question, and also match dot product of two subsequences. That's all from me. I hope that, and for sure the codes of C++, Java and Python is down below if you want to take care, or else you should code by yourself for sure. That's all from me. I hope that you guys liked it. See you in the next video. Take care. That video was legit way too long, right? 35 minutes. Damn. I don't know how you will respond to that, but I try to keep it as brief as possible. Cool. See you in the next video. Take care.